Hello, my name is Larisa Sogacheva. I'm working at Finnish Meteorological Institute in the climate research group. We are doing the aerosol retrieval using the AESA instruments. And here I would like to present the project that we have been working since 3 years already. This is the Aerosol-CCI project. So I will tell about the project itself, about the validation procedure, and the results obtained during the project. So the goal of the ESA climate change initiatives project is to initiate and produce the essential climate variables using satellite data, and those products, they have to follow the GCOS requirements. As for users and advisors, here we talk about the climate change community. And this ESA-CCI project is focused on the European satellites, but other American satellites are used also for validation and for comparison. There are 13 different CCI projects, among which aerosols we are participating in. So Aerosol-CCI, it started in July 2010, so it's already the 4th year of the project. We work closely with the Aerocom community for the data, for the product validation. And what's very important and very useful and very interesting in this project, that this is the first project where I personally participate with the independent validation teams. So we definitely validate our product before we deliver it, but this is kind of home validation. But besides this validation, we have 3 different institutes, so Aerocom is one of them. Also, the institute in Lille has been doing validation of our product, and the Empire Institute in Germany. And initially, this project is focused on the understanding of the differences between different algorithms and the very important focus on the algorithm improvement. Here is the Aerosol-CCI partners. So DLR and FMI are on the top because the project leaders are from those institutes. So Kerry Lilly from our institute and Thomas Holzer from DLR. So besides we have the Institute of Bremen for Mary's instrument, Oxford for AESR as well, Swansea AESR. This is the COMOS, I think the PSI Institute, NIL for validation, and Max Planck for validation. And what's very important here, so the main message that Aerosol-CCI project, it brings together most prominent European aerosol retrieval teams, retrieval groups, with also non-European groups contribution. So the main concept of the project was to understand the difference of various projects, have the, as I already told, have the independent validation team, and integrate major European teams into one team. About the Aerosol-CCI project, here in the middle you see the list of the instruments of the satellites participating in the Aerosol-CCI project, and on the left are the variables retrieved using the satellites. On the right side is the coverage for which we are getting the data. So if to go briefly, this is mainly aerosol optical depth and Angstrom coefficient from the AESA Mary's folder, and only GOMOS for AAI and stratospheric extinction. Why those upper and lower part are colored with different colors. So we are now at the final stage of the first part of the project, and now we can conclude that the parameters which are colored with darker color, they meet the requirements, the user requirements, so they are ready to be used for the modelers and in the other climate community. And the product which are on the lower part of the table, This product is delivered, but the uncertainty of the product is not enough. I mean, the quality of the product is not good enough still to be used in the climate research, and the improvements are still needed. The steps of the step of the analysis, the step of the project was, first we had to improve the algorithms. We had several workshops and we did several experiments on that. So we discussed the optical models, cloud masks, surface treatment, and post-processing. The next stage was that we selected the algorithms and run 4 months round-robin exercise. So this was needed to choose the best algorithm for the 17 years of reprocessing of the data. Also, we worked on the selection of the ECB products, and all the steps that we have been doing, the same validation tools and statistics. During all steps, the same validation tools and statistics have been used. So the final product is level 2 and level 3 data. The difference is the level 2 has the 0.1 degree resolution, and level 3 is 1 degree resolution data. So the validation teams, they calculated the global and regional statistics. Also the scoring, which includes spatial and temperature correlation, has been done, and the validation against IRANET and MODIS, MISR, Calypso has been performed. We had several working groups working on the, as I already told, on the aerosol models. So we choose the common aerosol models to be sure that the input to the models is the same, so the results can be compared. Also, we discussed the non-spherical dust particles. So we discussed aerosol climatology and surface reflectance treatment, and there was lots of effort has been to the cloud detection and screening improvement, because for the aerosol retrieval, it's a very important task to get the fully cloud-free pixels to retrieve AOD. And the last point that we also have had a discussion with the other CCI project, which is the CloudCCI. So we discussed the consistency between the aerosol and CloudCCI cloud masks. Briefly about the aerosol components. So we used 4 different aerosol components in all the algorithms, and if you want to read more about that, to know more, you can open this Lubovic et al. Paper. We use the aerosol chromatology, which has been prepared for us by the MPI Institute of Meteorology Institute in Germany. This climatology has been derived from the 12 different global models. So we studied, as I've already told, we studied the consistency between aerosol and CCI cloud masks, and this is another task for us for the future, to understand why do we have the different cloud screen in these 2 projects. So why the cloud screening is different. About the algorithm improvement, this is the plots for the maps for the AOD retrieved during the different steps of the algorithm. So on the top, you see the AOD maps for the baseline algorithm, the algorithm that we had at the beginning of the project. Then after implementation of the common cloud mask and common aerosol model, so we had considerable improvement for the AOD. On the left, the vertical line belongs to the one algorithm. So the left one is the ATSR ADV, which is our FMI algorithm. The other one is also the same instrument, but the other algorithm, it's the ORAC algorithm. Then the next column is also ATSR, but Swansea University. So you see how, even though the instrument is the same, you see how different were the algorithms at the beginning of the exercise. So and after implementation of the common thing, so the maps look slightly more close to each other. And this is the final AUD maps. About the analysis tools, so as I already told, the level 2 data has been validated at ICARI in France. So the level 2 has been validated against Aeronet and against the different satellites. So the other validation was the MPI scoring. I will show the plot, the figure later, and the other is the Aerocom model intercomparison for level 3 data. So this is the picture for the scoring that has been done at MPI. So the spatial and temporal resolution, the spatial and temporal validation is done here. So the correlation has been calculated, and the color says how good or how bad the retrieval is comparing to, for instance, MODIS and MISER. So unfortunately, I can't say much about this, but anyway, this is one of the tools to validate the data. I mean, to calculate the temporal and spatial correlation. Also, with the same tool, we can follow the improvement of the algorithm. For instance, here is the comparison of the baseline for Swansea against Aeronet, and this is, I think, this is the this is comparison between the latest Swansea version and the base slightly Swansea version. So the darker the color, then the I mean, if the dark blue means that the algorithm performs better after the implementation, and the dark red says that the algorithm performs worse. So as you see here, so the performance of the algorithm has been increased considerably to the better numbers. And this is the Aerocom interface. So this is the interface developed at Norway, and this is extremely good and very powerful instrument to compare the algorithms. So, for instance, in this figure, you see the performance of the different algorithms, different ATSR instrument, the performance of the different algorithms. So here you can choose which algorithms you want to compare. Then next slide. So you can either plot maps from all the results. You can plot the difference map. You can see plot the histogram or scatter plot, or see the score or series. So you just have to choose the name of the instrument, the name of the algorithm, and then you choose the period of the comparison and what you want to compare. So this is the AUD of 555, and there are different plots are chosen here, so that's why you can compare those two figures. But you can compare, for instance, scores for different algorithms. It's very easy and useful tool. For instance, here, if you choose the scatter plot comparison, you immediately see the difference between the algorithm with the related statistics. So here's also the same, the scatter plot comparison. What else has been done by the Aerocom? So when we do our kind of home validation, we can't actually I mean, if we do our validation and then if other team makes the validation, then the numbers are not. I mean, the numbers we are getting, they not always mean the same. But what Aerocom has done, so he made the common point filtering. The number of data points have been reduced, but after that procedure, we know that we're comparing like apple to apple. So we have the same coverage, we have the same temporal resolution of the data. So and then the statistics are comparable. So what can we see from here? So here Aerocom compared the 3 different algorithms to Miser and Modis, ACO, and there. So here you see the number of observations. It's the same because we use because Aerocom uses this common filtering thing. So the correlation is about the same, but there are some difference. And according to this analysis, the correlation with AeroNet for all ATSR instruments is bigger than correlation of Modis instrument. This is kind of the good evidence that our data are compatible with what the Modis represents. And this is also the common point filtering analysis for. Sorry, this was the result for land, and this is the result for our ocean. So also rather good correlation, and number of observation is lower because the AeroNet Oman station are much sparse over the ocean. But again, the conclusion for all ATSR instruments that in general the correlation is high. This is the example of the monthly analysis, monthly statistics. And the question that we wanted to ask you during the project was if the 4 months analysis representative for the 12 months. And the question, the answer was yes. So it's not you do not need to have at least for AUD data retrieved from satellites. You do not need the monthly means for the whole year to prove to show the goodness of the algorithm. But if you have but the statistics for 4 months chosen for different seasons, so those statistics are enough. So after the validation of the 4 months, the validation for 12 months has been done, but the result of the validation it didn't change. So this is also another tool to see the improvements over precursor AUD dataset. Scoring is used here as well, and the maps generated at the Aerocom for the comparison. We also evaluated the pixel level uncertainties. But here I would say we have a big question mark, because the problem in the maybe not only our community, but maybe it's the common problem that all the teams, they have been calculating uncertainties in their own way, in their vision, in their own vision. So that's why those uncertainties, they are not comparable between all the algorithms, and this is the task for us during the coming phase, is that we are planning to have the workshop and to discuss what should be included to the uncertainties, what the uncertainties are. So it's very important for us to deliver uncertainties which are used by modelers in their studies. So the next validation was it was not the validation, but it was the comparison of the global AUD time series. On the upper graph, you see the time series of the AUD retrieved with ATSR in blue against the AeroNet in black. There are no numbers, but visually, and on the lower panel, it's the AeroNet sun photometer against Modis. And if you make just the visual comparison, the comparison between our AUD retrieved with from ATSR, they're in many cases they are closer than comparing to Modis. So that's another evidence that AOD retrieved with our European instruments, they are not worse, and sometimes they are even better. They are closer to the ground-based measurements. This is the regional time series for the ATSR AOD retrieved with Swansea against Ireland. So for the North Africa, the comparison is also quite good. For the East Africa, the difference is a bit higher. For North America, it's almost 1:1 with some outliers, and for the Europe, also the comparison is quite good. So also the stability has been investigated, and from this plot in red there is the Swansea AUD, and on the other colors it's in WF and MODIS data. So the stability, I mean, this plot says that RMS is quite stable except for years like 2004, and if the ATSR differs a lot from MODIS, so the same we see in the ECMWF modeling number. So overall achievements of the project. So we had the very significant improvement of the algorithm towards the GCOS requirement. As the output, we produce aerosol optical depth and stratospheric extinction, which meet the requirements. The other conclusion is that another achievement is that ATSR time series for the 2003 to 2012 are consistent with the IRONET. And another improvement that the product we deliver now, it consists the auxiliary information on the individual pixel level uncertainties, which is important for modelers, as I already told. So we improved our cloud mask. We improved consistency with the cloud CCI, but still there are some differences that have to be investigated. So the activity is that ECMWF and Mach 2 they are planning the data assimilation of the AOD retrieved in the early 2014. I know that the exercise has started already, and they are quite satisfied with the results. So we are doing about the same, and sometimes we are doing better than MODIS. Also, the inter-comparison to other satellites is planned. And we continue the aerosol cloud interaction study, which started at DLR. Problems limited length of ECV dataset, but this is the problem which relates to all the satellites, most of the satellites. Lessons learned from the project. So we have the critical mass of experts, and this improved. This was the very strong part of the project. We proved that the 3 steps is meaningful to improve the data set. So we have the baseline comparison, we have the round robin comparison, we have the validation, and the final validation. So those 3 steps are official and enough for I mean, with such 3 steps, we made so we made the algorithm have been improved considerably. So during the round robin exercise, we proved that it's enough. The statistical significance with 4 mass of global set is enough. We also proved that 3 ATSR algorithms they perform almost equal. But to use those results together, we have to think about the harmonizing of the uncertainties. As I already told, the uncertainties are presented, but the further consolidation and harmonization of the uncertainties is needed. Also, further work is needed on the surface treatment and cloud screen. The main advantages of the product that have been produced during the project is that the product is of the high accuracy. The coverage of the time series that can be used for which the algorithm can be applied is the years 1995 to 2012. So we can get the AUD for such a long period using the European instruments. Also the information content is rather high, so we get the absorption quantity, and also we get the vertical stratospheric product from GOMOS. And this is the documentation which is freely available about the Aerosol-CCI project. And all the data there in the open public access at the website. So the key publications are the one is about the evaluation of 7 European satellites in the for the AUD retrieval, and the other is about the aerosol retrieval experiments. So those papers are published. Other are in preparation. And phase 2, it has already started since 1 month. So we are planning to retrieve those characteristics with the same sensors and cover the whole available period of data set. And which is also very important. So we have to look again at the uncertainties and provide the common uncertainties. And then few slides, maybe it's introduction to the new community, which is the International Satellite Aerosol Science Network. It's the unfunded, open, independent, and international network of aerosol remote sensing scientists. It is in the close collaboration with other related initiatives, which are IRCOM, ICAP, and IRONET. So the goals of this organization is that to promote the use of satellite data, archive, keep the open archive and activity exchange of the information available. Yeah, and this is the website of the Aerosol. Please go and see. Maybe you find there something interesting for you as well. Thanks.
Questions? What is the temporal resolution of this product?
It depends on the instrument. For ATSR, it is okay. No, we deliver level 2 and level 3 data. Level 2 is 0.1 degree, and the level 3 is 1 degree resolution.
No, my question was what the resolution in time, so sampling time. Is the product available every day or every week? Or?
We deliver the daily product, but the coverage of ATSR is much lower than the MODIS. So you cover the globe in 5 to 6 days with ATSR. So we deliver the daily data and also average the monthly numbers.
Other questions? Also, can you comment on the link between aerosol and orbital? I mean, retrieval.
Actually, this
aerosol and they use 0.1. Your map is not 0.1. But the simultaneously you do the retrieval of aerosol, you need the surface reflectance. That's actually
yeah, it depends on the instruments. For instance, for the ATSR, which we are using here at FMI, so this instrument, it has 2 views. And with the K ratio, you don't need to know the surface reflectance. You use the ratio to eliminate the surface reflectance. And what we actually do, we have been retrieving AUD as our main product. But recently we started to retrieve the surface reflectance using the AUD as atmospheric direction. So the weakness is that we can't calculate the albedo because of the ADSR coverage. We don't have enough measurements for all zenith angles. But I have compared the surface reflectance retrieved for ATSR geometry. I compared it to MODIS and compared to ASRVN database. So it's the numbers are very high. I mean the correlation is like 0.8, 0.9. So for some instruments we do not need the surface albedo. For MARIS and for others, yes, the surface database is needed. This is the problem. But for ATSR, we are lucky. We don't need the surface characteristics to retrieve the AUD.
So you said something about the pre-define the aerosol types. How is that done? Do you assume for different regions different aerosol types?
For this we use the AUD climatology, which is built on the historical. It's historically based using the different aerosol models. So in the most of the algorithms we use the mixing ratio between the different aerosol types. So the ratio between fine and coarse mode for absorbable, non-absorbable aerosols, it's predefined. But for instance, in our ADV algorithm, we do not need this. So we calculate the mixing ratio inside the algorithm. So we are looking for the best fit, and then we don't use the predefined aerosol climatology. So the algorithms they are different, but I mean the results show that the end product is quite good for all of them.
Other questions from other people? Maybe another one from me. You said these 3 different algorithms, they produce similar results.
Yeah.
But to my eyes, they are not really quite similar. At least from just a visual comparison of the 2 maps, global maps. Are these the? So you have the ADV.
Just a second. Yeah. Yes, this is the final map.
This is final from the 3, but they are different instruments.
Oh no, it's the.
And if I look at ATSR, the second row, the red 3, you have a CREC, you have a SU, and you have a CINAIR, and then on the left is ADV.
This is the ADV, then the ORAC, then Swansea, then CINAIR.
They do not look similar to me or to that.
Well,
I'm sorry.
At least if you take the ADV, which is the our algorithm, and compare it to MISER, to MODIS and Parasol, so you see exactly, you see the features.
Okay, I agree.
Yeah. But if you take the statistics, the statistical performance is about the same. Actually, it's not the final version, but the intermediate. But if you want to see that, if you want to see the difference of our algorithm, this was our baseline.
Yeah.
This is what we are getting as intermediate result. There is a huge improvement.
What is the scale to maximum?
It should be to 1.
Okay.
0.9 red. But the difference in the algorithm, it actually can be seen here. So we don't retrieve the bright surface, but Swansea algorithm, which use the same instrument, so they do the bright surface. But they are weaker than we are in the some other regions. So there are advantages and disadvantages in all the algorithm performances.
But I thought this algorithm from Swansea, that's from original son of Peter Morse, huh?
Mm-hmm.
They assumed inversion surface.
Yes, yes, they do.
That is not correct, of course. There are some issues there.
Mm-hmm.
But I haven't worked on this for many years, so I should stop asking questions. Okay.
Yeah, we can discuss later. So.
Yeah, we did some review of other stuff some years ago. Okay, interesting. Okay, any other issues? No? Thank you very much.
Thank you.
Say hello to Ferret.
Okay, I will.